linear constant coefficient differential equation. Okay, we call it as higher order LCCDE, linear constant coefficient differential equation. So just to recall what we discussed yesterday, right? We'll write the general form once. The general form is as follows. Okay, you have d to the power n y by dx to the n plus, I can have, so you can have a number here. This could be an, this is an minus 1 d to the power n minus 1 into y over dx to the power n minus 1, and so on. You can have up to, this is a1 dy by dx plus, this is a naught into y should be equal to some function phi of x. All right, this is what is called as LCCDE, and since the highest power is n, this is said to be nth order. So higher order in the sense anything more than 1. Okay, 2, 3, 4, 5, n could be any number. If you have something like this, right, we will call these kind of equations as linear constant coefficient differential equation of nth order. N should be greater than 2. Okay, now what we do here, if you recall yesterday's steps, we have substituted d as the d by dx. Okay, this actually implied that the d square is actually equal to d square by dx square, and so on. I can write d to the n as d to the power n by dx to the n. All right, so this is what is called as a differential operator. This d is called as a differential operator. So we use differential operator to replace this. So what we did, we replaced that. So after the replacement, we are going to get an, okay, this is capital D to the n y, okay, plus a n minus 1 capital D power n minus 1 into y, plus I get a1 capital D y plus a naught into y. This is equal to RHS. We are not going to touch, we'll keep as it is. Okay, now, so I understood that there is something common. I am going to take it out. So this will be an d to the n plus a n minus 1 d to the n minus 1 dot dot dot. I'm going to take out a1 d plus a naught. This is what remains inside after I take out y equal to phi of x. Right? So what I'm going to do here, I'm going to call this function as, say, a function of d. Right? So this implies, now I can in short I can write this is a function of d into y is equal to phi of x. Okay, now in order to, when I solve this equation, right, I have an answer for y. Okay, so this is the differential equation. We are still in the differential equation itself, right? So this solution, right, the solution of this kind of differential equation, okay, I'll write, is y. The y which I am supposed to find out, right, that will be the answer. Okay, now how do you find this answer? This answer is pretty straightforward. There are two parts. The parts are y is equal to yc plus yp. So this is called as the particular solution. Why it is called particular solution? Because it depends on what is the function that is present on the right hand side. For example, if this is sin x, the answer is different. Instead of sin x, if I have something like e to the power x, answer will be different. So that's why we write it depends on phi of x. And the yc, this is called as complementary. Okay, this is complementary solution, right? This is independent of phi of x. We don't want phi of x for that. Okay, independent of phi of x. So when I say independent of phi of x, even if there is phi of x, I'm going to make this equal to 0 and I solve. Okay, because it is independent of this. So whenever an equation is given, right, any type of differential equation is given, my answer will have two parts. Okay, if the two parts depends upon, right, whether there is phi of x present or not. If it is not there, only yc I find out, that's my final answer. If there is a phi of x, I have a different approach to solve. Okay, right. Now what are the basic types of differential equations, right? We'll find out now. So the basic solution of the differential equation starts with finding out the complementary solution. To find yc, right, we look at the steps now. What are the steps you need to follow to find out the solution for, right, yc? Only yc we'll see first. Okay, so this is to find yc. Any equation given, will follow the following steps. Okay, so in the given differential equation, make phi of x equal to 0. That means, right, anyway, I'll start with the same steps like earlier. I come till here. Okay, you come till here, and if there is a phi x, make it equal to 0. That's the step. Okay, in this particular line I'm going to make that change. All right, let's do that now. So we said that, okay, please make phi of x equal to 0. This implies, right, I'm actually continuing from where we stopped earlier. I'm going to get a f of d into y is equal to 0. Okay, f of d is equal to f of d into y is equal to 0. So in this case, I know that my y cannot be equal to 0. I cannot say y is equal to 0, right? What I do, I will write an auxiliary equation, right? Yesterday's steps you recall, because we have done the same thing, but there is some additional parts to what we did in the last class. So I'm explaining that once again, right? Because there is some extra parts to be added. Okay, so write the auxiliary equation. What is the auxiliary equation? If you remember, replace d by m. Okay, I have to make sure that y is not equal to 0. So f of d should be 0. But I cannot write f of d equal to 0 because d is an operator. There is no meaning for writing an operator's equation. So what we do, this implies I'll write the auxiliary equation f of m equal to 0 is the AE auxiliary equation. Right? Recall what was the answer yesterday. We had something like m square plus 3m plus 2 equal to 0. We solved it, right? So now we write the next step is solve the auxiliary equation to find the roots. Okay, when you solve the auxiliary equation, you get the roots. Now the yc depends upon what is the type of root. Okay, so now I'll write once again. Select the yc can be directly written. You can write the yc directly by looking at the type of roots. what type of roots you get, because just now you see the last step says that find the roots, solve it and find the root. Now what type of root it is, we'll see the types now. Depending upon what type of roots you have, right, you use a table. I'm going to write a table now, and I will be able to write the yc easily. Okay, just to make it easy, we'll write a table. Okay, so yc can be directly written by looking at the type of roots using the following table. I'll give a table. This makes things very easy. Okay, so the table has, say, two columns. Okay, and on the left hand side I'm going to write the type of the roots, type of roots of the auxiliary equation that comes on the left side, and the guess of the yc. So how the yc is going to look like, you can make a guess. Okay, so the first type is roots are real and distinct. In a sense, roots are real values, 1.5 minus 1.5, 3 by 2, right? Anything which is real, okay, and distinct. In the sense, a root is not repeated, is distinct. Okay, you have different roots like m1 comma m2 dot 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 up to mn. Why n? Because I have nth power. Okay, so you have nth power means it expects n roots. Okay, so if that is the case, the yc which I'm going to guess is equal to, right, first constant c1, a constant into e to the power first root m1 into x. See, m1 is used, plus c2 e to the power second root m2 into x, plus dot dot dot, like that. I write all the roots, and finally I come to the last term, that is cn, nth constant, some constant c1 c2 c3 like that, cn into e to the power mn into x. So this will be the first category. Okay, that's the first case. All right, this is done. Let's go to the second category. The second category of roots are real, but they are repeated. Real and repeated. Okay, so all the roots are repeated, let's assume. In the sense, I have m different roots, right? m1, that's equal to m2. In the sense, all roots are 2 2 2 2 only. I have 4 roots, all are 2. Okay, it's of that type. m1 equal to m2 equal to m3 equal to m4. Every root, let us assume it is same, mn, that is equal to a constant value, say m. Some m is 2, like that. Okay, something. If this is the case, then the yc we are going to guess will be of the following type. Okay, this is, right, I'll start with some c0 plus c1 into x plus c2 into x square plus dot 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 dot, right? I am supposed to write n number of terms. Okay, n terms. So what happens, this is one less than that will come into picture. So this is c n minus 1, right? Because since you are starting from c0, it is n minus 1 into x to the power n minus 1, this whole term into, I'm supposed to write a value or at this location, but since there is no space, I'm going to write it below. Okay, so this is the answer, into e to the power m into x. So if you recall the yesterday's problem, we solved using this technique only. Whatever problem we solved yesterday, this was the basic idea behind the solution. Okay, all right. Now let me go ahead the third case. In this case, you see only three cases are there. The third case is number 3. So roots are complex conjugates. They are complex conjugates. Complex conjugates they're referred as m is equal to some real value plus or minus I into q. Okay, so p plus iq is one root, p minus iq is the other root. In such case, your guess of yc will be like this. This is always e to the power real part, e to the power px. Multiply this with a constant c1 into cosine value of the imaginary part into x cos qx plus a c2 another constant into sine value. This is sine of qx. So what are p and q? We already know, right? In the root, in the root obtained, if it is complex, I know that p is the real value which comes over here. The q, which is imaginary part, is going to come here and here. Okay, c1, c2 are the constants. So using this technique, we can obtain the yc. There is a special case. I'm going to write that as well. Rarely this comes even in the exams. So let's write the fourth case. And the fourth case is actually a special case. Okay, so the fourth case is complex and repeated. So the roots, what we are going to write is going to be complex, but they are repeated. Okay, so let's write that case. If it is repeated, then this is how we are going to solve. So all m1, m2, etc. we can write it like, so say roots m1 equal to m2 equal to dot 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 up to maybe mn, right? Everything is equal to m. That m is actually complex. M is equal to p plus iq, p plus or minus I into q. This is the format. All the roots are same. This m, which is p plus or minus iq, is repeated so many times. Okay, then the guess yc will be like this, right? Yc is e to the power px. No problem with this. This is as it is. Then what I write is going to change now. So if the roots are repeated n times, I am supposed to write n minus 1 terms inside. So c naught plus c1x plus dot dot dot. This is plus c n minus 1 time cn minus 1 into x to the power n minus 1. This is my first term. Multiply that with cos term, like the previous case. You see, cos of qx. Alright, this is the first part. So this into the cos qx is the first term. Alright, plus the one more time, once again, maybe you just have to differentiate. So I don't write c naught, I write c naught dash. C naught dash, this is c1 dash into x plus dot dot dot. Last term is going to be cn minus 1 dash x power n minus 1 close the bracket into sine qx. Okay, so you can see the similarity over here. This was just c1 into cos, but the c1 is replaced by this whole thing now because the root is repeated. This into cos. Similarly, the c2 which I had earlier, I'm going to replace it with once again one more set like this into sine. Okay, so using this technique, we can get the yc. So yc can be directly obtained by simply referring to this table. That's all. Okay, let me close this bracket. Fine. So using this table is very important. If you remember the table, you will be able to solve any question given for finding out its roots. Okay, so one straightforward way to do that. Let's go with some examples. Like, okay, so The question is, I'm going to ask, find the solutions of following differential equations. So whatever equation is given, we are supposed to solve this now. Okay, what I do, let's write the first question. Question number 1 is d cube y by dx cube minus 2 times d square y by dx square plus 4 times dy by dx minus 8y is equal to 0. Okay, so in this case I can see that the right hand side is completely 0, which means I don't have yp at all. Okay, only yc will be there, and that itself is a final solution. Okay, so what I do, my first step is always replace the d by dx in equation by d. So this means it is d cube y minus 2 capital D square y plus 4 times capital dy minus 8 into y equal to 0. So I take y outside now, common, that is d cube minus 2d square plus 4d minus 8 into y is equal to 0. Okay, so just to make things clear, let me go back and show that what we discussed, right? So the same steps we are following, you can check that now. So we have replaced this, right? Replace the d by dx as d to the powers now, then take y common from that, and whatever you have is what we called as this, right? So that's what we called as f of d, and on the RHS we assume that there will be some phi of x. So if there will be no phi of x, right, you can simply replace it by 0. That's what we did now. You can see that right hand side is 0. Okay, so as per the same discussion, right, this will be your f of d. Okay, but anyway, so I can directly go ahead and write the auxiliary equation, right? Because auxiliary equation is the one which can be used to find roots, because as d is an operator, you cannot solve. So replace d by m, that is m cube minus 2m square plus 4m minus 8, right? Equate that f of m to 0. Okay, now what I do, I try to find the root of this equation. I'm expecting 3 roots because m cube. All right, so what I do, let me take a m square out from the first 2 terms. I'm going to get a m minus 2. Okay, from this take m square out. Fine. Plus in these two, I'll try to take m minus 2. If you want, you take say 4. Take plus 4 outside. Okay, so when I take 4 outside, 4 into m is this, 4 into minus 2 is 8, equal to 0. Okay, so I can see that the m minus 2 is common. Here I have m minus 2, here also I have m minus 2, which means I can take m minus 2 outside. Okay, m minus 2 if you take outside, what remains? M square remains in the first term, plus 4 remains in the second term, right? This is equal to 0. So whenever there is a product and you equate the product to 0, either of the term has to be equal to 0, then only the product is 0. Otherwise both of them have to be equal to 0. This implies either m minus 2 equal to 0, this is one possibility, or the other possibility is the second number, that is m square plus 4, so the second term, this has to be equal to 0. So if the first term is equal to 0, I obtain m equal to plus 2. This is my one root. The second root, m square is equal to minus 4. So m is equal to plus or minus root of minus 4. Right? If you remember, the root of minus, if there is a minus term that is coming under root, it is replaced by I. Complex number. Okay, it's not complex, it's only imaginary now. So this m is equal to plus or minus root 4 is equal to 2, and there is a minus inside, it is I. Okay, so this is 2I. So I got two roots here, one root on the other side. That's why I told I am expecting how many roots? I am expecting three roots. The power is 3. So one root here, two roots here. So 1 plus 2. So totally I am getting 3 roots. Okay, so let's proceed. So before proceeding, I'll simply write the roots I obtained. So what are the roots? Therefore, m is equal to, the different roots we obtained are 2 comma plus 2I comma minus 2I. Okay, now let's go back. Let's check the steps. So to find yc, we did this. F of m equal to 0. This is what we did. We took the auxiliary equation, and in the next step it says that solve the auxiliary equation to find roots. Now we did till here. We obtained the roots. The next step it says that use the following table, identify what types of roots you have, and write the yc. Okay, all right, let's go ahead. Let me check the roots once. So this root is a real root. Okay, this is real root, not repeated. I don't see any other 2 in my equation. Whatever 2 you have, they are actually imaginary number. So I have one root which is real and distinct. So whenever you have a real and distinct, I use the table. Okay, I go to the table just to verify the first case. If the root is real and distinct, the yc will be a constant into e to the power m1 into x. m1 is 2 now. There is no m2 to mn in this case. Only m1 is 2. So I can write this type of yc for the first root. Okay, so my yc I'll start writing now. So I'm expecting a constant into e to the power the root into x. Okay, so let me write that now. So this implies, in a sense I am referring to the table and writing this. This implies yc is equal to, for the first root it is a constant into e to the power that root, that is 2 into x. But it's not over. It's not that I have to plus something will come. That something comes because of 2 more roots. But now when I see the roots, I understand that they are complex conjugate. So complex conjugate should be p plus or minus iq, p plus or minus I2. This is how it looks like. So the p is equal to 0 and q is equal to 2. Right? Let's go back to the table. So this is what is the second category. The second root falls, the second and the third root, they are under this category. Okay, and what is your solution? The solution you are going to write according to this notation. Okay, so I am supposed to write e to the power px, but in this case if you see that the e to the power px is the p, what I see there is a 0. Okay, since that is equal to 0, I am not going to write that, right? And but q is there. I still have a q value is there for this given particular problem, so we can write that. All right, so let me go to the solution now. So for the second case, it is, I'll follow the same notation, e to the power px, but e to the power 0x, which is 1, e to the power 0, which is 1, right? Into, I have to write, I'll just rub this. Okay, now what I'm supposed to write, this, take another constant. C1 is already used, you can use C2. C2 into, this is cos qx, q is 2, cos 2x plus C3 into sine 2x is your solution. This is the YC of the given problem. Okay, very straightforward. Just follow the steps, use the table, you get the answer. Okay, again, you need to practice a little bit so that you get familiar with what are the possible types of roots you are going to get. Okay, all right, let's proceed. Let's go to the next question. Okay, this is the one. The next question is, this is d cube y by dx cube plus 6 times d square y by dx square plus 11 times dy by dx plus 6 times y is equal to 0. Okay, so I know that my steps are very they're going to remain same, so I directly go to the next step. This is d cube y plus 6 d square y plus 11 dy plus 6y equal to 0. This means you can write d cube plus 6d square plus 11d plus 6. This into y will be equal to 0. Okay, this means I can write the auxiliary equation like this. This is m cube plus 6m square plus 11 times m plus 6 equal to 0, right? So now let me check whether we can factorize m cube m square. If you take m square out, I don't have a m square on the other side. No, this is not possible. We cannot factorize this using the manual technique. What I have, either I have to use a calculator, scientific calculator directly, you can get the answer. Otherwise, my next option is to make the table. Okay, so what I do, I find one of the roots, right? Let me say m equal to 0. When m equal to 0, 0 plus 0 plus 0 plus 6, this is not equal to 0, so not a root. Next, I'll go put m equal to 1. So this is 1 cube plus 6. Okay, then plus 11 plus 6 not equal to 0. When I have plus 1, I'll go to minus 1 now. Okay, so this is minus 1 cube is minus 1 plus 6 minus 11 plus 6 equal to 0. So you see that m equal to minus 1 is one of the root. So for making the table, I should know the one of the root. I have to get to know about one of the roots somehow. Only when you know that you can do this. Okay, so what I do, I write the root here, whichever root I found. Then I write the coefficients of the given equation. So 1 into m cube, 6 into m square, 11 into m plus 6 into m power 0. I write this. Now I know that below this always I write 0 and 1 plus 0 is 1. Next I write 1 into minus 1. That answer I'm going to write here. 1 into minus 1 is a minus 1. Then I'm going to add 6 minus 1 is equal to 5. Now 5 into minus 1 is minus 5. So 11 minus 5 will be a 6. 6 into minus 1 is minus 6. So this is equal to 0. So now you use this, and below this I'm going to write the powers 1 less than the current power. So you can see the in the current equation I have the highest power as m cube. So now I need m square, m and 1. In the sense m power 0. So this implies now my current equation becomes m square plus 5m plus 6 equal to 0. Okay, now what I do, this can be solved. M square plus 2m plus 3m plus 6 equal to 0. This is easy to factorize. So what I'm going to do here is this. I'll take m outside. This is m plus 2. Second term, I'll take 3 outside. Once again, you have m plus 2 left over. Now you can see m plus 2 common. First you take out my mistake. M plus 2 outside. M plus 2 if you take out, what remains is am plus 3 equal to 0. So this means either m plus 2 equals to 0, or the other option is m plus 3 should be equal to 0. Where if you consider the first one, the m is equal to minus 2. At the same time, if you consider the second one, it's going to give m equal to minus 3. Okay, so m equal to minus 2 is one answer, m equal to minus 3 is the other answer. Alright, now I'll write all the roots what I have, correct? So the first root we got already earlier at the top we have that is equal to minus 1. Next root is minus 2. Next root is minus 3. So we have how many roots? In this case we have 3 roots. And I just have to refer to my table saying that which category it belongs. If you see, they are not equal, they are not complex, but they are real. They are real but not repeated. So this belongs to the first case. So what is the first case? The yc will be equal to a constant e to the power minus 1 into x, first root, plus another constant e to the power minus 2x, plus another constant e to the power minus 3x. So you can see that each of these roots are present: minus 1, minus 2, minus 3. This is what is the rule says when we filled up the table. So simply referring the table, simply solving the differential equation by you obtaining a auxiliary equation, you solve it, get the roots, check what category the roots belong to from the table and write the answer. Very straightforward. Okay, now let's go and solve one more of the same type. Okay, and let me say, okay, let's go to slightly difficult question. The question is, d cubed y by dx cubed plus y equal to 0. Okay, now as a standard procedure, we write d cubed y plus y equal to 0, right? This means the d cubed plus 1 equals to 0 into y. My mistake, I take a y common. So from this I write the auxiliary equation. The auxiliary equation is nothing but m cubed plus 1 equals to 0. Okay, now I can check that one of the root is right. I can check that m cube. Okay, so put different values of m now. Put m equal to 0. This is 0 plus 1, that is not equal to 0, because I need one of the root with me, only then I can solve it. Alright, so then I put m equal to 1. Okay, when you put m equal to 1, this is 1 plus 1, that's also not equal to 0. I'll go to the negative side now. M equal to minus 1. This is minus 1 cube, which is minus 1 plus 1 equal to 0. So one of the root is minus 1. I come to know. Okay, what I do when m equal to minus 1, I use the table once again. So start with the root, that is minus 1. Then you write the equation. You can see that the equation is m cube plus 0m square plus 0m plus 1 equal to 0. So your coefficients are 1, 0 into m square, 0 into m, and 1 into this term. So that's how you are using this. Okay, just check that once. Now, below that, always write a 0. 1 plus 0 is 1. 1 into minus 1 is a minus 1. Okay, 0 minus 1 is minus 1. Minus 1 into minus 1 is plus 1. So 0 plus 1 is 1. 1 into minus 1 is a minus 1. So I got a 0 here. So I need to use these three. Since the highest power of the equation in the previous step was m cube, now this will be m squared. This will be m and this is 1. Right? When you multiply with them, I'm going to get my second equation as the m square minus 1 into m plus 1, equate that to 0. Okay, I equated it to 0 now. Now I need to solve this equation, right? Again, I can guess one of the root and I can simplify. Otherwise, my best method, what I suggest is to use the standard equation. If the highest power is 2, you can go with the standard equation. M is equal to, right, minus B, right? So if you want to check the values, A is equal to 1 because A into M square, then B into M. So B becomes equal to minus 1. That's actually present here. This is B. And C is equal to plus 1. Okay, so you are going to use this now to solve the equations. I'll rewrite this part. Okay, so this is M square minus m plus 1. So m is equal to, my equation is minus b plus or minus root of b square minus 4ac by 2a. So substitute this minus b, so this is 1, plus or minus root of b square minus 1 square is plus 1 minus 4 into a into c. 4 into 1 into 1 is 4. Okay, whole divided by 2 into 1, which is 2. So the m becomes equal to now 1 plus or minus root of, you see that this is minus 3, correct? This is minus 3 whole divided by 2. Alright, so this is equal to, this is 1 plus or minus root 3. I can write root 3 itself, but it is minus 3. Minus 3 is I. Okay, minus is I, root 3 I keep as it is, divided by 2. So what are your roots? We have two roots, 1 by 2 plus or minus I root 3 by 2. This is one root, or the second root. Okay, I have written both together, plus or minus, so you don't have to write a or. Sorry. Okay, so these are the other two roots. One root was already we solved, that is minus 1. The second and the third root of this equation becomes like this. Alright, let me write down the roots once again so that I can write the yc directly. Therefore, okay, let me write the y ones, not y, m ones. The root is equal to 1 minus 1 and half plus or minus I times its imaginary root 3 by 2. Okay, now if you want to write yc, the first root minus 1 is real and distinct. It is not repeated anywhere. It's distinct and it's real. So I can directly write c1 e to the power minus x. Okay, then if you check the other roots, the second and the third roots are complex conjugates. So whenever it is a complex conjugate, I am supposed to write e to the power real part. In the sense you can see that this can be equated to p plus or minus I into q. So p is real, q is imaginary. P is half. So e to the half x multiply with, right, a constant. C1 is already used, I use C2. C2 into cos qx. What is q? Root 3 by 2 into x. Plus another constant C3 into sine of, right, root 3 by 2 into x. So this is the final answer. So refer the table and get back to the answer.